Good morning, my YouTube viewers. I haven't made a video in a few days because I've been sick, but I can't stay in bed anymore because my back is hurting. I've stayed in bed so much. So I thought I'd try to make another video. And what this video I'm making now is the solution to the e.coli class imbalance dataset. This is a very hard data set to use, which is why you don't see very much on it on the internet, because people they just want to work on data sets that are easy, but this isn't an easy data set to use. This is the data set that I got from Jason Brownlee's site, but he did some things that I don't really agree with. He just said that on the classes where you only had two, just go ahead and delete those classes. But I don't really think that's a good idea, because that really defeats the purpose of machine learning, and it defeats the purpose of data science if you just delete what you don't like, or you delete what's hard to solve. So we'll go ahead and go over this data set and go over the solution to the data set. So this is what I copied from Jason Brownlee's website, just a little paragraph. The data set describes the problem of classifying E. coli proteins using their amino sequences in their cell localization site. That is, predicting how a protein will bind to a cell based on chemical composition of the protein before it is folded. The dataset is created to Kenta Nikai and was developed into its current form by Paul Horton and Kenta Nikai in their 1996 paper entitled A Probabilistic Classification System for Predicting the Cellular Localization Sites of Proteins. In it, they achieve a classification accuracy of 81%. And I won't read the rest of it, except to say the data set is comprised of 336 examples of E. coli proteins, and each example is described using 7 input variables calculated from the protein's amino acid sequence. So it tells you what the amino acids are, and it tells you what the proteins are. So the first thing that we're going to do is we're going to load the libraries, which we did. And then we're going to load the data sets. And then what I did was I gave names to the columns on the data sets, because the data sets didn't have columns on them. So I gave names to the columns. So you can see the data set after I've loaded it and gave the column names. So what we do is we check for null values, and in this instance, there are no null values. We do a graphical representation of the data set, and so you can see how the different examples relate to each other. And then we compare the result with independent variables. So I did a group bisection there. So what we did was we label encoded the result. So now all of the results are label encoded by using the label encoder. One thing we did was we counted each class. So class 0, we had 142. Class 1, we had 77. Class 3, we had 2. Class 2, we had 2. Class 4, we had 35. Class 5, we have 20. Class 6, we have 5. And Class 7, we have 52. So that's how many examples we had of each class. And you notice we had 2 examples of Class 3 and Class 2. And what Jason Brownlee suggested was just to delete those samples. But I don't know. I don't know if that's a good idea. It depends. If you want to get a really high accuracy, then go ahead and delete the samples. But if you don't want a high accuracy and you just want to make sure that you get all of the samples included in there, then I would say don't delete the samples. Now, I didn't delete the samples. Jason Brown deleted the samples, but I didn't. So now we do another group by session just to see how many we have of each. And yep, it's the same. So now what we do is we check the percentage of the results. So 0, we had 42.38%. 1, we had 22.98%. 2, we had 59. Less than 1%. 3, we had less than 1%. 4, we had 10.44%. 5, we had 5.97%. 6, we had 1.49%. And 7, we have 15.52%. So now what we do is we graphically represent the results. We had 8 different results, so you can see how the results are graphically presented in the disk plot. And then here's another disk plot that it tells you about all the different all of the different how all of the examples fit in and where they fit in to the data frame, really. Now what we do is we assign our x and y values. So y is train.result and x is train.result. Axis equals 1, and we want to see the shape of the x and y value. The next thing we do is we split the training set up for training and validation. So we use train test split for that. So x train x val, y train y val equals train test split, x, y, random state equals 27, test size equals 50, stratify equals y equals yes. Stratify, if you have a class imbalance, you're supposed to put stratify on yes, because that's supposed to help balance it out. And now what we want to do is we want to check the shape of the x train x val, y train y val, and so you can see that we've checked the shape of it. Now we have scaled it. We've put the answers on the standard scaler. So scalar equals standard scalar fit x train equals scalar transform x train, x val equals scalar transform x val. So we just scaled the independent variables. We didn't scale the dependent variables. And now what we do is we use the counter to see how many examples we have in the x val. So 0, we have 71, 1, we have 39, 7, we have 26, 4, we have 18, 5, we have 10, 6, we have 2, 3, we have 1, and 2, we have 1. And the next thing we do is we set up our class weights. And so this is a formula that I found to set up the class weights. And so, but we do set up the class weights. So whenever you're using one of the models instead of balanced, you can always put class weights instead, and that's supposed to be better. And now what we do is we do a disk plot on the y-val to see the y-val, see how the y-val is showing up. And now what we do is we define our model through all of my experiments, and I did quite a few experiments. I found 2 models where it picked up all 8 examples. And since that was the idea was to pick up the examples on the imbalanced data set, I decided that these 2 models that actually picked up all 8 of the examples would be a good solution. So Gaussian MB picked up all 8 of the samples, and it had 86.83% on the X train, Y train, and 80.9% on X-val, Y-val. I put it on the counter, and the counter, it picked up all 8 examples of the class. And then I put it on the confusion matrix, and it picked up all 8 of the class in the confusion matrix. We did a plot, and it picked up all 8 in the plot. So that was a good solution, and it was 80.95% accuracy on the X-val, and that was these people who actually wrote this paper on the e.coli website. They said that they only got 81% accuracy, so I've got the same accuracy of the people who actually developed this CSV file and wrote a paper on it. The next model that we used, where it picked up all 8 examples of the classes, was the Xgb Classifier. It got 100% accuracy on X train, Y train, and it got 82.14% accuracy on X-val, Y-val. And it picked up all 8 of the examples of the classes. And so we put it on the confusion matrix, and on the confusion matrix, it picked up all 8 as well. And so, and then we put it on a graph plot, and on the graph plot, we picked up all 8 as well on the graph plot. So that's it. That's it for this solution. I mean, I performed copious amounts of experiments on different models and different variations of models, and trying to use SMOTE and trying to use different variations of SMOTE, and this was the best I could do. This was the best solution that I could come up with. So that's it for it. That's it for this. What I can do to show you all of the what I can do, I know it's going to take a second to do it. What I can do is to copy and paste something from Google Sheets. It'll take just a second to do this. Hopefully I can. It says it's still loading. What I'm trying to do is I'm trying to copy and paste something from Google Sheets, just to tell you how much work I did. And this isn't including SMOTE and the class imbalance and things like that. Well, it was supposed to be it didn't turn out the way I wanted it to turn out, but it was supposed to be an Excel spreadsheet. But obviously, this Excel spreadsheet didn't turn out the way I wanted it to turn out, and I can't show it to you because because the screen recorder I have is only lets you go onto one page of Google. But what I'm going to do is I'm going to do a blog post and discuss the solution to the E. coli data set, imbalanced data set. And what I'll do is then I'll put it in there, because it's going to take too long for me to do a screenshot and copy and paste the screenshot onto this page while you're sitting here watching it. So I'll just do it on the blog post. So that's it for the presentation website. If you like this video, please like, subscribe, and share. If you like the work I've been doing, please, I've got my email address for my PayPal account in the description, because I don't have enough subscribers for to monetize. So the only way I can make money on this channel is to ask for donations. And thank you so much for watching my video, and I look forward to making a new video for you.